Good morning, everybody. Welcome to round 653, Div3 round. Not rated for me, but I'll be competing anyway. See if I can solve set. That's the goal, obviously. Today it was written by Vovu and Mike. So I don't actually know how to pronounce this guy's name. I've always said Vuv in my head, but I don't think it's Vuv because I'm just skipping the last two letters entirely. But he's very popular. We have company. So yeah, I think I'm gonna make a public version of my bot that other people can use for announcements, because I've heard that it's a pretty wanted thing, which makes sense. It's a lot nicer than having to refresh the page like a Neanderthal. Anyway, good morning and good luck, have fun to everyone who's competing. Given x, y, and n, you need to find the maximum k between 0 and n such that k mod x equals y. Can n be huge, right? So k mod x equals y. Is y less than x? Yeah. So you just take out a lot of y's. Yeah, so I guess there are just two cases. Okay. So int x so n over y is how many full times you can get. So if y times plus x is less than or equal to n, then this out y times plus x. Otherwise, this out y times minus 1 plus x. I think this should be right. X, y, oh, I have these backwards, I guess. So this should be y and then x. I'll explain the solutions to all problems at the end as well, assuming I solve all of them. 15, double 6, not right, huh? Oh wait, maybe it is right. Just didn't hit enter. Yeah, okay, so we're fine. Awesome. Oh man, I missed the 1 minute or the 2 minute solve.
Well done, sir. Is beyond compliment.
So you're given n, in one move you can either multiply n by 2 or divide it by 6. So find the number of, okay, impossible. So if you can multiply it by 2 or divide it by 6, that means the only thing that matters is the number of factors of 3. So that means it needs to be just a multiple of 2s and 3s. Okay, so int n2s equals 0, and 3s equals 0. We also need to count how many factors of 3 it has. So if n2s is less than n3s, or is greater than n3s, or n is not equal to 1, and this out -1, because that means we won't actually ever get there. Otherwise, there's a unique way of doing it. We have to print the minimum number of moves. So this is going to be so it's going to be this out n3s minus n2s. That's how many extra 2s you need, plus n3s. 0, -1, 2, -1, -1, 12, 36. 36 is a lot of moves, but all right. I don't think we need print writer for that. I think we should be fine. Given a bracket sequence of length n, where n is even, consists of this many opening brackets and this many closing brackets. In one move, you can choose exactly one bracket and move it to the beginning or the end of the string. You choose some index, remove that character, and insert it before or after. Okay, yeah. Your task is to find the minimum number of moves to obtain regular bracket sequence. It can prove that the answer always exists. Does it always exist because we have the same number? Yeah, we have this many opening and closing. So what we need to do, whoa, it's so small. It's just the most negative the answer gets, right? That's it. So this is -1, this is 0, this is -1, this is -3, yeah. So yeah, you can think of bracket sequences as like a sequence of pluses and minuses. And if it's like a close, then you can think of it as a minus. Then otherwise it's a plus, and then you just want to keep track of the smallest it ever gets. And I think that's going to be it. Maybe not. Yeah, so we have this. We go through each character. So this should be a minus and then a plus, right? Okay. So it's a close. Should be -1. Okay. Oh, this should be, yeah, the minus min. Then we should be good. Awesome. The reason you can do that is because you always just move things to the beginning or the end, and then you move, I guess you always move the negatives to the end. That would solve the problem. So that should be fine. All right, zero remainder array. You're given an array of n integers. Initially, you have an integer x. During one move, you can do one of the following operations. Choose some integer and increase that thing by x, and then increase x by 1. Or you can just increase x by 1. I see. The first operation can be applied no more than once to each index. Interesting. Are we just waiting on? Okay. You need to find the minimum number of moves required to obtain such an array that each element is divisible by k. So, cool. Minimum number of moves. Yeah, so each, yeah, okay. So each number in the array, if you can only add once, then you have a unique number that you have to add under some mod, under mod of k. And you can like greedily assign that and then just take the max of all things that you've added. K can be really big, which I suppose is unfortunate. but I think that should probably be fine. Yeah, I'm not too worried. I think we can implement this without thinking about it beforehand. So we're given n and k, and then the array. So now we need to go through each element in the array. And we're gonna need some hash map, I think. Okay, and now our ans is going to be 0. So now for each thing in the array, we need its value under mod. So int, I guess we just all we care about is its value, right? So I mod equals k. That determines pretty much what we have to add. I guess that's more important. So int to add equals k minus I mod k plus k mod k. This is what we would have to add to it to get it to work. Does it start at 1? Initially it's equal to 0. Yes. Okay. So now, let's make this, well, okay, yeah. So make this a long, I guess. Or, okay. So if times used, well, let's count. So times equals times used, I get default. We need to get the amount we need to add. And by default, it'll be 0 because we won't have added it before. So then times use dot put to add times plus 1 to add plus equals k times. So we need to skip this many full cycles. And then ants equals math.max ants to add. Yeah, I think that should be fine. Okay. No, am I always off by 1? I'm not really that close at all. So in the first example, we need everything divisible by 3. So it takes 6 moves. Yeah, so really we've got 2, 1, 2, 0. So what, I guess initially the answer is, well, if 2 add is equal to 0, then we can just continue, because we don't have to add anything to it. I guess that was one thing I was missing. So now we can start the answer at -1 and then add 1 to it at the end, and that will handle the fact that it was 0. So 6, 18, 0, 227, 8. So I think we've handled all of the interesting cases at that point. How many test cases? Not too many. So let's try submitting. And I think I'm comfortable enough with that to move on. Oh, interesting. An easy hard version. Are actually different problems, so read both statements. I guess I will read both statements then. Thank you for the announcement. So there's 104 days of summer vacation, and Alice and Bob are playing a game. They want to play and joy. I love to joy. It's my favorite part of the day. Her mom doesn't think that they love to play and joy. It's not Very understanding of her mom. Was there any point in this entire paragraph? Okay. There are n books in the family. The ith book is described by 3 integers. The amount of time it takes Allison and Bob to spend to read it. 1 if they like this book, or 0 if not. Oh, whether Alice likes it or whether Bob likes it.
Problem he got wrong answer test 5, sir.
Oh, man. Alright, so now we pause and think for a minute. Yeah, I guess I take a look. Alright, wrong answer, huh? Initially, you have some integer x. During one move, you can... Yeah, okay, so what's the biggest number you need to use? They all need to be equal to 0 modulo k. How big can these things get? 10 to the 9. Should I be scared of overflow? Maybe. So an integer, is this always positive? Yeah, it is. Well, I guess we can change this to this equivalent thing. The max of the ants, or 2add plus 1. Takes this many turns. So for each thing, if it's equal to 0, then we're fine. Otherwise, get the number of times, add 1 to it for the future. 2add plus equals. Oh, that's an issue. Yeah. Oh, I'm stupid. Okay. So that was some overflow issues. Yeah, that was overflow nonsense. Darn. Well, okay, that's fine. Back to reading. Back to reading our book here. It's funny, this problem about not liking to read, and this is the entire this is the problem statement, right? Okay, so you have a bunch of books. Alice likes some, Bob likes some. They take different amounts of time. You need to choose a bunch of books from the n books such that Alice likes at least k books of the set. Bob also likes at least k. Oh, and you have to pick m. The total reading time of these is minimum. After this is true. Do we need to do this first condition, and then after we do the first condition, do this condition? Yeah, I don't think this is clear to me. I think I'm going to ask a clarification. So my question is, do we need to minimize the total reading time after making sure that each likes this many books? Or is it like different in that we need to minimize the reading time regardless of the set we choose, and then of the things with minimum sets, we need to make sure the first quantity is also satisfied? What is the difference between this and E1? Wait, is that not what I was just reading? Oh, okay. Well, that's the minimum amount of time. Is this what the set is? Yeah, okay. So the first one is find the answer. The next one is print the set.
Well done, sir. AC on. Also B.
Problem E, right? I thought it said D. Oh, D. Okay. Yeah, so the only difference is that you need to extract the set. Well, we can delete ones that are 0 for both because those are never helpful. So now we have 3 types of books. We have 1, 0, 0, 1, and 1, 1. I don't see how this is any easier. Maybe I'm crazy. But yeah, I don't see... Initially, I don't see how to do this problem without just finding the answer. Like finding out what it is. But I suppose I get double points if I do that, right? So that's not a bad thing. This is ICPC style screwing, right? Yeah. Okay, so initially you have like, well, you only have these 3 types. We can mostly get rid of, like, as we go through. If we see one that only helps someone who's full, like take if it doesn't help. If it does help them, I guess we need to skip it if it's unhelpful, right? If it just helps one person. Okay, that's the same with one, it's the same with the other. Now what if we have a 1-1? That's the tricky part. So if it helps either, then we want to take it. Otherwise, oh, and we also need to pop, yeah, okay, so I think this is easy. We want to minimize the total reading time of the books. Yeah, okay. This is a good problem. I don't like how it's worded, but the idea of the problem is good, I think. It's interesting. It's like feels kind of at coterie to me. what am I doing? Type up here. Is this how many we need to pick? Do we need to pick K books? What is K? Oh wait, do we need to pick? Oh, that's the difference. In the second problem, we need to pick a certain number of books. Right, we need to pick exactly M books. Yeah, that's the difference. So this one is easier. Well, let's just solve this first. Yeah, okay. So now well, we need a book. So now we need our books. And then we need to sort them. So now we have all of our books and we have them sorted. So now int a have equals 0, b have equals 0. And now we need, I guess, a priority queue.
As you're hearing you work, sir.
We have company. We have company.
Understood, sir.
So we need a priority queue for the books that A has, and also a priority queue for the books that B has. And then, once we have these, we need to go through all the books. I'll just need a long total of 0. Okay, so now we have all of these books. So there are 3 cases. So if not b.a and not b.b, then this is worthless. If b.a and b.b, this is both. Else if b.a, else. Okay, so if we have b.a, if A have is less than K, or need happy. So if we need this, then we'll take it. If we don't need it, there's no reason to take it. So then pqa.add b, and total plus equals b dot time. Yeah, so we'll remove the smallest from these. We want to remove the biggest. So yeah, now we'll return the biggest book, the least helpful one. So if the one that A has is less than is less than what we need, then add this book and add this to the total time. So the same thing we want to do with this, but just kind of backwards. And we also need a have plus plus, because we have one more A book, and B have plus plus. Okay. So now there are a couple cases. So if a half is less than k or b half is less than k, then I need to just call this k. Then we need to just keep it. So total plus equals b dot time. And yeah, so don't add it to either priority queue. But if a half is greater than k and not pq a dot is empty, then look to remove equals pq a dot remove. Total minus equals to remove that time. A half minus minus. Otherwise, well, I guess this is just if b half is greater than k and pqb is not empty, then we did the same thing, but from the other priority queue. All right, so if we have both, well, if we need one of them, all right, cool. If, yeah, I think I got that. All right. So now we've handled that well, I think. Otherwise, we might need to remove from both at the same time. So int bonus will be equal to pqa dot peak dot time. Oh, if not pq a dot is empty. Oh man, this is annoying. We need to, because one of them might be empty, but the other might not be. Okay, so if they're both not empty, then int bonus equals pqa dot peak dot time plus pqb dot peak dot time. And then if bonus is greater than b dot time, then pqa dot remove, pqb dot remove, and total minus equals bonus, total plus equals b dot time. Now these are going to be similar, but slightly different. Yes, but also no. Okay. So if A isn't empty, it's just going to be this. Then remove from A, and we're fine. Okay. Otherwise, B isn't empty, but A is. Then we remove from B. And if that's helpful, then we want to move from B, take out the bonus, and add back in the time. Oh, what's up? What's up here? Class cast exception. Sort books. Does books not implement comparable? Comparable. Look. 24. Darn. Can we get a smaller case that's broken to... Oh, it might be impossible. Okay. Let's handle the impossible case first. If A halves less than K or B halves less than K, then sys out -1. Otherwise, we can print the total. Okay. So we're here now, right? This is what we're left off with. time. And then at the end, it's probably helpful to print of state. So we print how many we have of A, how many we have of B, and then I guess the total. So first we look at a book with cost 1, probably this one, I guess. So we take it, and then we take it. So total cost 3, we have 0A and 2B. That's odd. Let's see, what case is that? That's this case right here. These are true, then A have plus plus and B have plus plus. Yeah. In this case we remove from both, so it doesn't matter. Well, I guess, yeah, that's fine. Now here, if this is the case, then B have plus plus, and now this will be A have plus plus. We'll have an extra one, 18. Well, I'm kind of excited now if this is right, because that means we're going to do the fun version of this problem. Of course, this has to pass more than these 3 easy cases, but we'll see. So I don't know who's out here solving F. Maybe some people are like speedrunning it or something. It's looking pretty good, I'd say. Given an array of n integers, in one move you can choose some index and shift the segment. Wait. Segment of length 3 cyclically to the right. Your task is to sort the array by no more than this many operations, or say that it's impossible to do so.
Well done, sir. Is C on problem B1?
Okay, so what happens if you do this? If you've got 1, 2, 3. Does the parity of the number of inversions stay the same? Man, E2 really is the wall, huh? It's interesting. Because it seems like so close of a problem, but it's, I guess, just way harder. Yeah, so I think the parity of the number of inversions is constant. Because if it's like you take this 3 and move it over by 2, so if they're both bigger or both smaller, you increase or decrease by 2. If they're bigger and smaller, then they're bigger and smaller, you don't change it by anything. Yes, that's the parity of inversions stays the same. So if the parity of inversions is wrong, it's impossible. So there are definitely cases in which it is impossible. Otherwise, we can just do it naively, right? So just like find the smallest element, shift it to the end, find the next smallest element, shift it to the end. So now we'll have the last thing in the last position. Then we get the next smallest thing in the last position. So then what could go wrong? Yeah, because then when we have 2 elements left, if there are an even number of inversions, these are the smallest 2 elements. Yeah. Okay, easy problem. That's a really cool problem, actually. I really like that problem. It's like super clear. Definitely need a parameter for this. So int a equals this thing. We have our array. Now we need to count how many inversions there are. Or wait, can we? Yeah, sum of n is small. Awesome. So 4 int I equals 0, I is less than n I plus 4 int j equals I plus 1, j is less than n j plus if a at I is greater than a at j, then increment this. So now if ins mod 2 is not equal to 0, then print -1. Otherwise, we're fine. So now we print the indices where we change, right? Yeah. So, and we can just do n cubed. Can we do n cubed? That's a bit big, but I think that should be fine. So, oh, is it a, wait. Oh, we have a problem. It's not a permutation. Or is it a permutation? It's not a permutation. So that's an issue because this could be interpreted ambiguously. That's why the problem is non-trivial, I guess. So we need to decide how we're going to sort it initially. And we want to decide how we're going to sort it in such a way that we have an even number of inversions. Yeah, has anyone gotten this other problem yet? I don't think I'm going to work on it, so there's not really much reason for me to care about that. But yeah, okay. So we can like we just care about the number of the number of things less than or equal to you before you. We want to see if there's any pair we can swap that will change the parity of that. Yeah, so let's do this. So static class element. So we want to compare this element's value with the other element's value. So first, we just want an array of elements, I think. We'll also keep them sorted. So now we have these two arrays, and now we can sort this sorted one. Okay, so now we have them sorted, so now we can assign their values. And we keep the original one to fix later. Alright, so now we have all of these things. So if elements at I is an elements. So if this one dot value is less than this one dot value, then it is I. So if this first one is bigger than the second one, then increase the number of inversions. Okay. So now we have counted the number of inversions, but we might be able to fix this by swapping too. So if elements at first dot this thing's original equals elements at second dot original. Well, if they're not equal, we don't care about this. Okay, otherwise they're equal. So int, well, then we need to count how many are between them, right? That's what's relevant. So int between equals 0. Yeah, so what happens? So the inversions that are before the first one stay. The ones that are between the second one, I guess all of those stay as well. Should we just do it naively? And then maybe TLE, but these are for loops, so it should be fine. Yeah, first end. Okay, so int first orig. Okay, well int what do we care about? We only care about elements that are between these two. So we care about things with value greater than or equal to first and less than second. And we only care about the ones in the range from like I inclusive to j exclusive. So if this thing's value is greater than or equal to elements at first dot value, and this thing's value is less than elements at second dot value, then if we swapped first and second, this would be a inversion change. Yeah, so then change plus plus break outer. We only want to do this if ins mod 2 is equal to 1. And if we do this, what happens? So all of these inversions actually increase. Yep. So ins plus plus, then break outer. Oh wait, no. Yeah, we don't want to do that yet. So now if changed mod 2 is equal to 1, then change the inversions by some amount, break outer. Oh, we also have to swap them. Yeah, let's do that. So, swap them. So int temp equals elements at first dot value. So first's value equals the second one's value. So this will swap their values. So now we need to resort sorted. Okay, so now if we still didn't find it, like if we ever found it, this would fix inversions. So now we won't hit this. Otherwise we do find it. So now at the end, we want to sys out indices dot size. Print all of the indices, and print a new line, I guess. This should probably be print writer stuff. Okay, so now we just have to actually do it, which I think I'll do in n cubed. Yeah, that doesn't hurt. Can n be less than 3? No. Okay, so 4 int 2, or I guess element to fix end equals n-1. So we're going to fix stuff from the back to the beginning. This is the element that we need to fix. So if to fix it so while index is less than n minus 2, and now if index equals n minus 2, then indices dot add. Well, I guess let's just do a swap, huh? Static void swap element array elements int index. So we have all of the things we need here to swap, and now we can do this. So indices dot add index. Let's keep track of it so we can print it at the end. And now int temp, well, okay, so we have the 3 elements. So now elements at index equals E2, elements at equals E3, rather. Elements at index plus 1 equals E1. Elements at index plus 2 equals E2. And now that should be fine. All right, cool. So if this is the case, then we need to swap these things, pass in the elements. The index is going to be n minus 3. That's in the indices. Now index plus plus. Okay, so while the index is less than n minus 2, index plus plus at the end, and we need to swap the elements from index to that plus 3. So that means this means it's n minus 3, so we can do, yeah, so that's fine. Okay, so we swap a bunch of stuff, then it should be fine. What does this actually do? Oh boy. This is odd. Guess let's go case by case here, figure out what is going on here. So we'll print the initial inversions, and And then I guess we should probably print the permutation too. Okay, so there are 0. Awesome. So now that may have actually been important. I should probably read it. Yeah, okay, that's what I thought. So trying to fix the thing at index 4. So we should be able to fix the 5 quite easily. Trying to fix the thing at index 3. Oh yeah, we don't want to move it to the end. This shouldn't be n minus 2. This should be to fix in, well, it should be, yeah, fix in minus 1. This should be to fix in minus 1. To fix in minus 2. Good. It's very, very right. Wait, how many solves? Oh, only 8. Okay, it's reasonable. That's a lot of debug. Yeah, so let's fix this. Not quite. All right, so now let's do a simpler one, maybe. The classic. How many inversions does this have? 1, 2, 3. Can we solve this, maybe? So if we have 3, 2, 1, well, you have 1 inversion here, 2, so that's 3 inversions. It's impossible. But 3, 1, 2 would be solvable. It's 1 inversion. That's another inversion. That's not the right permutation at all. Sorted at I, that value equals value. 2, 1, 1. So what happens if you do 1? If you do it once, then it's 2, 3, 1. Yeah, do it again. That's right. Okay, cool. All right. Sounds a bit more plausible. Let's just try this one, and then maybe I'll submit to see. 1, 2, 3, 3, 6, 4. So I'm saying the fourth one. 1, 2, 3, 4. So do that. Then you'll have 6, 3, 4. and I'm saying do the third one, then you would have, yeah, then that would work. Alright, yeah, I'm gonna submit and go to the bathroom, and we'll see what happens. Alright, solid. So now we're just left with problem E. Shouldn't be too bad, I don't think. But we'll see. Actually, it's kind of difficult. Like, I shouldn't say that because it's like the same, roughly the same difficulty jump from E1 to F as it was from F to E2. And F is definitely just like, the hard part is just the implementation, not anything else. So, it could be hard. Alright, let's take a short break. Look at my friends, see what's going on. Not bad. John's struggling a little bit more than I'd like to see. But other than that, pretty much expected. Alright. So my vacation has started, so Alice and Bob want to play enjoy. Oh yeah, this one. The mom doesn't think they enjoy playing enjoying. I don't know. I don't know what kind of mother that would be. The mom thinks her kids are all sadistic. So in this case, books that they both hate are fine. Like, those might be important now. Because maybe you read a couple books that you like, and then after that, the only reason you read it all is to fulfill the mother's requirement. Maybe we can build off the answer from E1. That's an idea. So if we have some set of books. And now we need to add to it. I guess we wouldn't have any 0, 0s. Now we need to add to it. So what could we do to add a book? We could add a 0, 0. I guess we could add any book at all, really. Yeah, so adding a 0, 0 would be one way of doing it. Probably a pretty good way. We could also like add a 1, 0 that we don't need. Maybe it's really easy to get all of the things Alice likes. We could also add a 0, 1 if we need to. But it might also be helpful to add a 1, 0 and also add a 0, 1 and also remove a 1, 1. And then I suppose we could also add a 1, 1. Those are the options. So at each step we find an augmenting book, I think, might be the idea. And we keep augmenting the cheapest way possible for as long as possible. Yeah, so I think it actually makes a lot of sense to have that first problem be E1, if I'm understanding it right. Because then E2 literally is like do E1 and do some other stuff. Okay, so Boolean used. So this is gonna be, I'm gonna have to go through this again and like clean it up a bit. This is kind of annoying. All right, so if here we have both books, so if it's helpful to at least one of them, then we want to use it. So then b.used equals true. A have plus plus, b have plus plus. And remove this, otherwise remove this. Okay. So this is if they aren't both, like if it's not helpful to one of them, that means we might be able to replace an existing one with a 1, 1. Are these ever even true? Let me think for a minute. I don't think these cases even matter. If this one thing's time is bigger, yeah, these cases don't matter. The reason these cases don't matter is because we're doing them in ascending order. So that makes it much cleaner. Okay, good. So, what is this? What's going on here? If we can remove from both a 1, 0 and a 0, 1 and replace it with a 1, 1, then it might be helpful. Okay, so book removed 1. B.used equals true. So this is add this thing because it's helpful, and then remove stuff we don't need. Same thing. Here we add this book. This is replace two things with one. All right, so now this is the case where it's one of these things. Okay, so if we need it, then we add it. So now then what is this going to be? B.used equals true, and this is also B.used equals true. Okay, we should definitely clean this up to make a add and remove method. So if b dot b and well, b dot a and b dot b, then it's both. Else if b dot a, else if b dot b. So in this case, then pqa dot oh, these need to be static now. Priority queue. Okay, so now we have these two things. So now pqa dot add b, pqb dot add b. If it's both, we don't need to add it to a priority queue. Oh, now we should probably have this total. Static total equals 0. So now, yeah. So if we add it, total plus equals b dot time. Otherwise, if we remove it, total minus equals b dot time. Okay, so now if we have this, if it's both, we won't worry about it yet. Okay, so now, this is just add b. Oh, we need this a have and b have, okay. A have plus plus, b have plus plus. This is a have plus plus, this is just b have plus plus. Now we need all of these things again. Okay. So now we add this book. Yeah. The reason I'm doing all this is so that I can just call this method, and I don't, like, it's much cleaner. And then I will probably make fewer mistakes. So then we add this book, and then remove. Oh, cancel. Remove to remove. And yeah, add A or add B. In this case, we also want to add B. So let's double check samples. -18, 8, -1. Good. Okay, so we've done all of this. Awesome. So now we need to repeatedly do some more stuff. So we need to either add the cheapest 0, 0, or we need to add the cheapest 1, 0, or add the cheapest 0, 1, or add these two cheapest things, remove that, or add this. Yeah. So we can have a priority queue of each type. Well, cheapest A, cheapest B, cheapest both, cheapest none. Cheapest A equals new priority queue. Thank you. B both none. Okay. So these will be things that are alive. And now we also need a priority queue of worst both of the things we've taken. Okay. So this is like untaken. These are all untaken things. And this will be taken. Awesome. So if it's becomes taken, then we don't look at it here anymore. But if this is the case, then worst both dot add B. Okay. In all other cases, we don't care that we've added it because we have no reason to ever remove it. But if we have removed it, then we might need to add it. So, well, yeah, in this case, we might need to add it. So, cheapest both dot add B. Okay. All right. So now, what is up with this? So now what do we have to do? So we need methods to get the cheapest ones of each of them. But we also need to add everything to all of their relevant priority queues. Okay. If B dot A and B dot B, then cheapest both dot add B, else if B dot A, cheapest A dot add B, else if B dot B, cheapest B dot add B, else cheapest none dot add B. So here we add it to the cheapest priority queues. So now we have to go back and fix stuff. Oh, we also have to print the answer. That should be pretty easy though, because each book keeps track of whether or not we're using it. Yeah. So if books at I.use, then syserror I equals a space. Is k is less than or equal to, or m is less than or equal to n? Okay, good. Wait, they have to read exactly m books? That's annoying. So that might not be possible for weird reasons. If you have to read exactly m books. Yeah, I might be reading too many books. Is it a problem? Yeah, that's gonna be an issue. So what I have to do first is, before I do this, I have to oh, this is obnoxious. Alright, I have to go to the bathroom. I'm wrong for a couple reasons. Like, alright, the first issue is that the way I'm finding the cheapest way of making sure that they both, like, this doesn't use the minimal number of books. I guess that's the only problem, really. So that's the first. Okay, so it's not really that bad. So we do this. This will get us the cheapest. This will get us the cheapest way of doing all these things. And now, if we use too many books, we should also keep that, right? So int books. Plus. So yeah, good. So we might have used too many books. which is really annoying, but I think that's fine. So while books used is greater than k, greater than m. What's the input format? Okay, so while the number of books we've read is greater than the number we need to read total. This is well, it's greater than the number we need to read total, then we need to remove, well, like, try adding one back in, because that's the only option we can do. Okay, so how do we do that? So we can do while static book get cheapest both while not cheapest both dot is empty, then cheapest both dot add or dot so if this is used, then cheapest both dot remove, otherwise turn next. And then, oh, what's going on? Okay, so now if this isn't true, then return null. So where was I? I'm here. So now book to add equals get cheapest both unused. So then we want to get the most expensive of each of the other things. Okay, so we want an unused one, right? Or we want a used one. So next dot used, it's not used, then continue. And next. Worst to be used. So this is the same thing, but with B. So we get the worst B. If it isn't used, then it should have been removed. Our worst A. This is worst B dot add B. Well, yes, we have the worst both, worst A, worst B. So if to add equals null or worst A or worst B is equal to null, then six out -1 return. Okay, otherwise we can make the swap. So remove worst A, remove worst B, add to add. Good. So we do some stuff and we're fine. Oh, and then that should update books used, right? Yes. So now we have the minimum number of books that work. So now all we have to do, how much time do we have left in this problem? 24 minutes. I know it's 24 minutes. So now all we have to do is add books as long as we need them. Or this isn't true. Okay. Now we might not have enough books. Okay, so while books used is less than read total, then we have to be careful here. So we need to, there are a couple of choices. So we might need to get cheapest none unused. Cheapest unused. Cheapest both. So while it's not empty, peak. If it isn't used, continue, blah, blah, blah. Okay. Get worst A, or get worst used with used error. Worst, what did I call this? Worst A. Worst B, get cheapest none unused. Cheapest none. Okay, well, I should probably check this. And then that should probably be fine. Okay, so now, yeah, I extracted the answer already, so that's fine. I need print writer. I might need print writer. Okay, so now I just need to add more books. So we're gonna need the cheapest none, cheapest A, and cheapest B. Okay, so book cheapest A equals get cheapest A unused book cheapest B equals get cheapest B unused. Book cheapest both equals get cheapest both unused. Book cheapest none, get cheapest none unused. Okay, so now we want to know what the best of these is. So let's make a method for that. Time less than or equal to that time A. Okay, so res equals better A B. Okay, so now we can get the min cost of all of these. What I call it, min cost, cheapest A, cheapest B, cheapest both, cheapest none. So now this is what we would normally add. Our other choice is to we can remove a both and add cheapest A and cheapest B. Get worst. Yeah, I guess we need worst both. Get worst both used. Okay, so now if worst both is equal to null, or cheapest A is equal to null, or cheapest B is equal to null, then we are forced to do best to add. Otherwise, if yeah, okay. Otherwise we have a choice. So now if best to add equals null, then we're in big trouble. This out -1 return. Okay. So otherwise we want to add best to add. Okay. Otherwise, if best to add is equal to null, this shouldn't ever happen anyway. But yeah, I guess just throw null for a minute. Okay, so now in all other cases, how much time do I have? 16 minutes. So long cost 1 is going to be equal to long cost best to add, and the best to add dot time long cost swap is going to be equal to cheapest A plus cheapest A dot time plus cheapest B dot time minus minus worst both dot time. ties matter. I don't think ties matter. Ties shouldn't matter. Yeah, I don't think they matter. If best to add is less than cost swap, then add best to add. Otherwise, remove worst both, add cheapest A, add cheapest B. What are the chances this works? Okay, so what do we have left to do? I don't need that. So I've got these arrays. So we have, I guess I should just have a worst none too. Worst none. Cheapest A, cheapest B, both none, worst both. Okay, cool. So now let's fix this. Okay, so else worst none dot add B. So we added everything. Cheapest both, cheapest A dot add B, cheapest B dot add B, cheapest none dot add B. Okay, so let's see if this is right. That would be amazing, wouldn't it? Oh! Well, that's interesting. So these all need to be +1, don't they? One, two, four. So I do 1, 2, 4. So what is my cost? They each want to read 1. They need to read 3 total. That is not right then. B dot used equals true, B dot used equals false. One, two, 4. Oh, it's because I sort them. Yeah. Alright, so now I have our unsorted, and now this needs to be if unsorted that I used. 1, 5, 6. 4, 5, 6. Let me go to the bathroom, I guess. All right, so that's I saw that one coming. Let's just say. So, well, I don't know why I'm checking the scoreboard because it doesn't have any impact on my decision making. Yeah. Okay. Sure. So one return. Oh. Ah. Yeah, that would do it. What else could be wrong?
Problem 2. Time limit exceeded test tensor.
Ah, because I'm an idiot. Come on, print router. That was, I guess, a bit unnecessary. Okay, why could that have been an issue? Yeah, it could have been. Throw null. This should never happen. Yeah. So what else do we need to do? How else can we speed this up? This should just be fine. That's not really this is quick, I think. We iterate through each book and do a constant number of things. This we always decrease it by 1 each time. Then this we either do this always, or we print -1 return, or we throw null, or we add 1. So this will always increase by 1 each time. So there are no infinite loops. It's just being stupid for not having fast input. If this TLE is, that'd be kind of sad. I guess worst none I don't need, right? Oh, damn. What about this?
Problem 2. Time limit exceeded test tensor.
Darn it, what? Oh, yeah, okay, this is wrong. So if not next.use, then pq.remove. Yeah, and I did it here, okay. So many submits. I'm glad it's not like wrong super quick. Yeah, okay, it was an infinite loop. So lots of maintenance is my opinion of that problem. I don't think I should have any time limit issues because I'm not using tree sets. I'm just using priority queues. Priority queues are the fastest logs in the world. It's n log n. There's no way you can do it faster than n log n, I can tell you that much. Okay, we're fine. It's definitely right. Come on, give me my points. All right. Well, yeah. So a fun contest.
Well done, sir.
There we go.
Easy on problem 2.
So what is the maximum we could place? 19th. Not bad. Not bad. This is just very unnecessary. I could have saved lots of penalty points there. I could be. I guess I could be like 15th. Yeah. If I just had one fewer submit, I'd be in 15th place. Alternatively, that would do it for me. Yeah, not the end of the world, I guess. So let's talk about problems. Awesome. Problem A. Yeah, okay, so problem A is, I don't know, kind of the classic problem A sort of thing. So you have to find the biggest integer mod, well, let me get the variable names here, right? Mod x that's equal to y. The biggest integer k, where k is less than or equal to n, some n they give you. The important thing to keep in mind is, like, if you imagine your mod is like a circle. So hypothetically, you've got this really big circle here. It's a bad circle. Let's try one more time. Cool, there's our circle. So if you walk a full time around the circle, then you will, I guess you're a full time around the circle. So now the question is, if you take n steps around the circle, you'll go around it possibly a bunch of times. And the question is, what's the last time you pass this position? So you can figure out the number of times you'll go around the circle in total, and that's just going to be n divided by x, because the distance around the circle is x, so the total number of times you go around the circle is going to be n divided by x, which means you're either going to go around the circle n divided by x times and then step until this red here, this red thing, or you'll go around n divided by x times and then you won't get to the red. And if that's the case, then you'll go n divided by x minus 1 times and then to the red. So it'll be this thing times x plus the value under mod, or it'll be this. So you just have to check, is this like small enough? If it is, that's the answer. Otherwise, you need to subtract one circle loop from it. Awesome, that's problem A. Let's look at problem B. Problem B was a cool problem. The title kind of gives it all away. So you have like some integer. Maybe your integer is going to be equal to like 2 times 3 to the third times 5. In a given step, what you can do is you can subtract out, like you can divide by 3. So you can divide by 6 rather. So you can divide by 2 times 3. If you do that, what you're left with is going to be 3 squared times 5. Because 1, 2, and 1, 3 cancel. So you can either do that. The other operation you can do is you can multiply it by 2. And if you multiply it by 2, you just add 1 to the exponent in the 2. So it should be pretty clear that you can only subtract 1 from both of these exponents at the same time. So the first thing you're going to do is you're going to increase this exponent until they're the same. If the 2 exponent is already too big, then you're not going to be able to get rid of one of these 1s. So then it's impossible. Also, yeah, so you'll have like 2 to the third times 3 to the third. Also, if you have any factors that aren't a 2 or a 3, it's going to be impossible because you'll never be able to divide out a 5 just by dividing out 6s all the time. So yeah, so you can check, is the exponent on your 2 smaller than the exponent on your 3, smaller than or equal to? And if it is, then you might be okay if you don't have any other factors. If you don't have any other factors, then you're definitely okay. If you have any other factors or your 2 exponent is too big, it's impossible. And if it is okay, like if it's possible to do, then the total number of steps is going to be, you have to turn this into a 3, so that's going to be 3 minus 1 steps. Then you also have to turn the two 3's down to a 0, so then that's going to be plus the 3 steps. So that's how you do problem B. Cool, contest is over. I guess let's check our place real quick. 20th place, not bad. Alright, cool. So problem C, move brackets. Yeah, so in this problem, you have a bunch of like brackets, a bracket sequence, I guess. But it's not a valid bracket sequence. You're just guaranteed that it has the same number of open and closes. So what that means is like you'll have some bracket sequence, and you can represent this bracket sequence as like pluses for an open or minus for a close. So if you imagine you have this, and every time you hit a plus, you add 1, and every time you hit a minus, you hit -1, then you start at 0. After this plus, you'll be at 1, then you'll be at 0, then -1, then you'll be at 1, then 0. Yeah, there you go. 0, then 1, then 0. So since you have the same number of pluses and minuses, you know this first and last number will both be a 0. And then what you can do is you want to make it so that the smallest number in the array is a 0. You want to make it so there are no negative numbers in the array. And what you can do is you can always just take the last plus and move it to the very beginning. And you know that that will increment all of these values right here. So the negative problem is going to be somewhere in here. It's going to be before this plus that we move, and it's going to be, I guess, after the first negative. Well, really, it'll be in this range here. We don't really care whether it's before this plus or not because we increment all of those numbers as well. But we know this will be where the negative numbers are. If this is the last plus, then the negative numbers will be in here because all of these numbers will be positive or 0. So yeah, so we can keep doing that, and the total number of things we have to move in order to do that will just be the biggest negative number. Like how negative it is, that's the number of times we have to move something. So we just keep track of what these numbers are and what the smallest thing is, and then we're done. Isn't E2 evil? It sure is. A lot of maintenance, man. Yeah. So problem D, 0 remainder array. Okay, this one is not too bad, I thought. So you have, yeah, I mean, like, I guess even just like look at how many people solved it. So yeah, like anyone blue or above should be able to solve it with no difficulty at all. So yeah, so basically what the problem's saying is like you've got a bunch of numbers in the array, and you need to turn each of them into a number that's divisible by k. So you're given some k in the beginning, and I guess the sample they give is pretty good. So if you have the numbers 1, 2, let's change a little bit. Let's do 1, 2, 4, 1. And then you want k to be, let's say k is equal to 4. So you want to turn all of these into a number that's divisible by 4, which means you want the value of all of these mod 4 to be equal to 0. So in order to get this to 4, or something divisible by 4, you have to add 3 modulo 4. To this, you have to add 2 modulo 4. To this, you have to add 0. And to this, you have to add 3 again. So the first thing we can do is we can get rid of all of the things that are adding 0, because those are already fine. That's an interesting case that might cause a bug for you. Because, yeah, I guess it's in samples, so it's not too big of an issue. And then after that, what we notice is that we're going to have to add 3 to this one, but we can only add 3 to at most one number. So if we add 3 to this one, the next number that mod 4 is equal to 3 is going to be 7. So this we can add 7. And then to this, we haven't added 2 to anything yet, so we can add 2 to this. So now we can just increment our counter, and we know when we've done this, we've had at most we've added each number at most once to a given thing, and we just care about what the biggest number in our group is. So it's that number of steps plus 1, because if we need to add 1, then first we need to make it 1, then we need to use the 1. So yeah, that's how you do problem D. Pretty straightforward. Okay, so E1, I guess we'll talk about E1, then E2, then F. So E1 was a pretty doable problem, I felt. So you've got 3 different types of books. You've got books that nobody likes. I guess there are lots of those out there. Then there are a couple books that only Alice likes, a couple books that only Bob likes, and a couple just like classics that everyone loves. So for these books, well, yeah, all right. So here's the first observation. So in this problem, you want like the total number of books that Alice likes to be at least K. And also Bob likes greater than or equal to K. And this is the only requirement in this first problem. So what we can do in order to make sure that happens is, the first thing is there's no point in reading books no one likes. Because the only thing we gain from it in this problem is we gain that like this person's read a book that they liked. If no one liked the book anyway, there was no purpose in reading it. So we can handle all of those by just ignoring them. Now we have these books left. So what we're going to do is we want to look at these books. We want to look at these books by value from cheapest to most expensive. So we're going to like go from cheapest, like shortest to longest, basically. Shortest book to the longest book. And now the important thing here is that there are only a couple cases, and since we're going shortest to longest, we're going to keep track of like the best answers so far with the books we've seen. So if we see one of these books of this first type, the only reason we would ever want to use it is if Alice wants to read it. And Alice hasn't read enough books already. We know all of the books Alice has read already are books that are beneficial for her to read. We're gonna assume that. So Alice would rather read all of the books she's seen already before in this list because all of those books are shorter. And she likes all of them as well. So we don't want to get rid of any of those books. We might just want to add this book, though, if Alice hasn't read enough books and this is the next shortest one she can read. So that would be a good reason to add this one. So we might want to add this. For the same reason here, we might also want to add this. Same thing, but for Bob. So if this is a book Bob likes, Bob hasn't read enough books yet, he should read this one. Okay, now the third case is if we have this. So this is the next cheapest book. If either Alice or Bob likes this book, then we should add it. But we have to be careful when we do this. It's possible if we add this book, we're adding this book because Alice is short on books. So maybe Alice doesn't have enough to read, so we added it for Alice. But then Bob might have this other shorter book that he has to read, but he's going to have to read this book anyway. Which means if Bob has already read enough books, we might be able to subtract books out from Bob's list of books, I guess. So we can subtract books out from Bob as long as he's read enough. And similarly, we can subtract books out from Alice if Alice has read enough after we've taken this one. The other thing we might want to do is it's possible that Alice has read a book she likes, Bob has read a book she likes. We might be able to remove both of those and add this one. So that's kind of like a fair trade. And we can do this fair trade if no one wants to, like no one needs to read this book to read an extra one to count toward their K. But it's possible if the most expensive one of these and the most expensive one of these are both like very expensive, they're both more expensive than reading the book we're about to read, then we can read this one instead. So those are the 4 different things you can do for E1. You can read book A, read book B, read book C, or you can remove one of these two, or remove both of those and add this C book. You also have to take care of, you might want to like add this and then remove one of them. Okay, that is E1. And I'm gonna do E2 now, even though it's probably harder than F. I think it's important to like keep this train of thought going. So E2. So for E2, now the constraint, there's like one other constraint here, which is like Alice has to read greater than, or Alice has to like greater than or equal to K books. Bob also has to like greater than or equal to K books that he reads. And also they have to read exactly M. So this constraint is very important and like makes the problem like noticeably harder. And we're going to handle it in kind of an interesting way. So what we're going to do is first we're going to do our E1 solution. And that will find the minimum cost to satisfy this. But when we do that, we may have read too many or too few books. So now we're going to have to adjust the number of books we've read in order to satisfy this condition as well. We want to do it with like, we'll either increase or decrease the number of books we've read by 1 at each step. And we'll keep doing that until we hit the correct number of books. But we want to like we're not allowed to decrease the number of books that Alice likes or the number of books Bob likes. Because if we decrease that, then we'll break this first condition. All right. So the first thing we can do is it's possible that after satisfying this condition here, it's possible we've read too many books. And I'm going to, like, for now, what I'm going to say is I'm going to say 0, 0 is a book no one likes, 1, 0 Alice likes, 0, 1 Bob likes, and 1, 1 they both like. So it's possible we've read too many books. If we've read too many books, what we have to do is we have to, like, combine a book that Alice and Bob read into one book. So then we have to, like, minus Alice, minus Bob, and then plus both. And that will maintain this condition as cheaply as possible, but it will also decrease the number of books we've read by 1. So this is the only way of doing that, because we can't, like, we're doing this for as little as possible. We're satisfying this condition for as little money as possible. And since we're doing that, that means we're not reading any extra books. So there's nothing we can just throw away. Because if there was, then we wouldn't be doing this, like we wouldn't have gotten E1 right, basically. So yeah, so this is the only choice we have if we're reading too many books. It's also possible that we're reading too few. And in this case, it's a bit more challenging because there are a bunch of choices and we have to be careful with which ones we can do. So the first choice is we can read a book that everyone hates, but read it just because we have to read more books. The second choice is we can read a book that Alice likes, or we can read a book that Bob likes and have the other one just suffer through it because we have to read books anyway. The third one is maybe there are lots of good books out there. We can read a book that both of them like, but not read it for the purpose of both reading books that they like. So not read it for the purpose of satisfying this K requirement. The only reason we're reading it is because we have to read M books. But it's possible that maybe there's some book that's really cheap that everybody likes. We can just read that one anyway. It's really short. Everyone likes it. We can just read it anyway. Like Animal Farm. Right? Great book. Everyone likes it. Short, quick, painless. I guess it's not really painless. The story's kind of painful. But anyway. So yeah, so like these are the 4 different options. There's also one more option. And that option is you can subtract out a book that everyone likes, and you can replace it with one book that Alice likes and one book that Bob likes. So if you do this, you've gained one new book, and you may have done it for a cheap amount because you've been able to get rid of this book here. So maybe it's cheaper to do this, just combine these two and have these two separate. But if you need a certain number of books, then this might be a beneficial trade to make. So you might lose a little bit of money on it here, but it's better than reading a new book for no purpose whatsoever. So these are, I guess, all of the different cases. So what you need to do is you need to do each of these optimally. So you're going to need to maintain a bunch of values, and the values you're going to maintain are going to be the cheapest and most expensive. So like the cheapest book that you haven't read, so cheapest like unused, and the most expensive you have used. Because every time you want to read a new book, it's going to be one you haven't used and you want to read it for the cheapest amount possible. And every time you want to replace a book that you were considering reading with 2 ones you haven't read, for example, in this case here, then you want to find the most expensive one you read, and you want to get rid of that, and you want to get the 2 cheapest ones that you haven't read. So, okay, so these are the things you have to maintain. You can keep track of these by using, well, one thing you could do is, like in C++, you could use a set. In Java, you could use a tree set. And you could, every time you read a book, or every time you say, I'm going to read this, you remove it from the tree set, or put it in the other tree set and stuff like that. I was worried about time limit stuff, maybe for no reason. Yeah, okay, I guess for no reason. I probably could have been fine otherwise. But yeah, so that would work with tree sets. Alternatively, you can have a priority queue, and every time you remove a book, you put it in this, or every time you use a book, you put it in this cheapest or most expensive used priority queue. Every time you unuse a book, you put it in this. You have to be careful to check to make sure that if it's in this priority queue, it's really used, though, because you can't remove from priority queues. So you have to be careful with that, I guess. So like when you're about to remove something, make sure, okay, this guy is actually someone who is used, or someone who is unused, depending on which priority queue is in. So if you maintain all of this, you can check these 5 things right here, and you can take the best of all of them. And you can just keep doing that one step at a time. And it's pretty clear that griddily taking like augmenting paths works here, because if you make a bad decision initially, you can replace that decision later on. So, and that's like all of the decisions you can make. All right, cool. So that is that problem. Problem E, E1 and E2. Finally, let's talk about problem F. I thought problem F was a good problem. So problem F is you had to sort an array, but you had to sort an array in an interesting way of doing it. So the array was like let's pick this one here. So 1, 2, 3, 3, 6, 4. So what you could do is you could pick some continuous range, and you could shift it all to the right. So the 3 would go here, the 6 would go here, and the 4 would go here. And you can do that as many times as you want. Well, all right, so here's the sub-problem that we'll ask first. So let's imagine this array is a permutation. When can we sort it? Well, if you've got a permutation, maybe you've got like, let's just look at 3 numbers that we're going to shift. So if you have 1, 2, 3, or really, like, what happens here is you take this 3rd number and you put it before the first 2. That's what changes in the array. And when you do this, there are, I guess, 3 different cases that can happen. So the first number, or the first way, is this can be like some number less than 3. This can be some number less than 3, and this can be a 3. Alternatively, you might have some number bigger than 3, some other number bigger than 3, and then a 3. And then the third option is you might have like a bigger than 3, and then a less than 3, or the other order doesn't matter, and then this 3. And the important thing to keep in mind is in each of these cases, the number of inversions that you change it by is even. So in this case, you add 2 inversions. In this case, you subtract 2 inversions. And in this case, you add 0 inversions. So what's an inversion? An inversion is like 2 numbers that are in the wrong order. So in this case, this 4 and the 6 are an inversion because the 6 is bigger than the 4, but it comes before the 4, and it should come after, right? So they're in the wrong order. If you have some array like 4, 4, 3, 2, 1, then every pair of numbers is an inversion. So those are all inversions, but also the pair of numbers that are 2 apart are inversions. And also the 1 and 4 are inversions. So you have 6 different inversions here. So anytime the number of inversions is odd, it'll be impossible, because we can only do these 3, like these are the only 3 things that can happen. In each of these cases, we change the number of inversions by an even number, if it's a permutation. So now what we'll show is if it is a permutation, we can always solve it if it is an even number. And the way we can do that is, like, let's say we've got a 4 and then some other numbers here. What we can do is, no matter where the 4 is, we can keep moving it right until it's in its last most position. Now we have three numbers and a 4 here. Now let's say the 3 is right here. We can take the 3 and we can move it to the right till it's in the second last position. So now we have a 3 here, and now we have 2 other numbers. We know these 2 numbers are going to be the 1 and the 2. We haven't done anything yet to keep track of what order they're in yet. We might have messed them up, it doesn't matter. But the important thing is, all of the rest of these numbers are all going to be sorted. And now we have a 1 and a 2 here. So if the array looks like 2, 1, and then a bunch of sorted numbers, if this is the case, then we have exactly 1 inversion left, which means it was impossible. But we know there were an even number of inversions, so this isn't going to happen. If there were an even number of inversions, by the time we sort the rest of the array after the first 2 numbers, these are going to have to be left in the right order. So that's the permutation part. Okay, so now we know how to solve the problem if it's a permutation. If it's not a permutation, we can coordinate compress, and if all the numbers are unique, then we can solve it. But the issue is, in this example that I drew up on the top, you might have duplicate numbers. And if you have duplicate numbers, you've got an issue. Here's why. This could correspond to 2 different permutations. It could be 1, 2, 3, 4, 5, 6 like this, or it could be 1, 2, 3, 4, 5, 6 like this. And if you look at these 2 numbers here, this creates like 2 different numbers of inversions. So we have to pick the right one of these. Like, we have to pick what final order we want all the numbers to be in. And we want to do that in such a way that the total number of inversions at the end is correct. Like, we want it to be even. And if it's even, we'll be able to sort it. If it's odd, we won't be able to. So we have to assign each of these numbers to some permutation so that the total number of inversions is even. We can do that. So like one thing you can notice, I guess, is that I won't prove it because it's kind of messy. I don't know. I won't prove it because I don't have a clean proof immediately, but it's very clear to me that if you have like some assignment of numbers, so initially we'll assign numbers like this. We'll just like in this beginning way here. And now we might swap the assignments of 2 numbers that are the same. So what we can do is just naively in n squared, we can count the number of inversions in this array. So currently we have just this 1 inversion here, the 6 and the 5. But then we want to have 2 inversions. So if we flip these 2, then we can make it the right number. So we'll have a 4 and a 3 here. So in order to check these pairs that we can flip, what we can do is we can check each pair of numbers. So we'll have these 2 numbers. We know the values of these 2 numbers are the same. What we care about is how many numbers in this range would like create an inversion kind of. So how many numbers are there in this range that, let's say we initially gave this number a 3 and now we gave this number a 5. What we want to know is how many numbers are there like in this part of the array that are between 3 and 5. Let's say initially both of these were like the numbers in this array up here, they were both 3s. So we know anything that's a 3 or a 4, anything between 3 and 5, we know all of these will correspond to 3s in the initial array. Now we want to know if we swap these 2 elements, how many inversions will this create or destroy? I guess they're only created if we do it in a certain way. But if there's an odd number of numbers here, then if we swap 2 of them, that will create an odd number of inversions. And I think you can always just, if you have any of these pairs and it's odd, I think you can just swap the first 2 and that'll always be fine. In fact, I'm pretty sure that's the case. So yeah, so basically, I think all you need to do is just say, if there are any duplicates and you have an odd number, swap 2 of them and then you're fine. I like countered it naively because n was small and it required me not to think, but yeah. All right, so that is solution to problem F. That's, I guess, all the problems from the set today. I thought it was quite a good set, actually. Like, as far as Div3s go, I thought this was a very interesting one. E2 was good practice, very at-coder maintenance-y, but still good. And yeah, we'll see. Hopefully I got 20th place. I'm pretty happy with that. So it looks like 2nd place for people for whom the round was rated. 4th place for Div2+. Or is purple Div 2? Yeah, I guess purple's Div 2. No. So if I were in Div 2, I would have gotten fourth. So, yeah, not bad. First page, right? That's what counts. Thank you for watching. Hope you guys enjoyed the round as well. And I will see you, I guess, the next time Codeforces is a contest. Goodbye.